Latin is for us like Sanskrit for you. It's the mother language. We in those times when I was a student, we had to study Latin. Everybody had to study. I studied 2 years Latin. And there is a Latin saying, errare humanum est, sed perseverare diabolicum. My English translation would be something like, to make errors is human. Everybody makes errors. But to insist in the errors or to repeat the errors is devilish. So I was behaving devilish there because I repeated it there.
But then you rectified your error, then. So how you describe that?
I hope I will be forgiven.
Yes.
By my devilish behavior.
Thank you. Hello. So in the last tutorial we saw something about separation theorems, which was in the morning session. You saw that separation theorem was used to prove a result. So separation theorems for convex sets are very useful in different fields of optimization. Now today in this tutorial we are going to discuss about optimality conditions, because optimality conditions are very important to identify an optimal solution of the given optimization problem. For example, for a linear programming problem, we know that if you are in this feasible region of a linear programming problem, one way is to find out the value of the objective function at every point of the feasible region and then compare those values and then find out the optimal solution. For example, if you want to find out the tallest student or tallest person in this room, then we can find the height of everyone and then compare, and then we can decide. But that will be a time taken process and may not be possible because this feasible region contains infinitely many solutions. So to find the value of the objective function at infinitely many solutions is very time taking, and it may take infinite amount of time to compare all these values. So then you know that we have a very good result that tells that this if there exists a unique optimal solution, that will be a corner point feasible solution. So that result actually exclude many points from the feasible region. And now what we can do, we just have to compare these 5 points in the feasible region, right? So with this infinite in place of comparing infinite number of points in the feasible region, we can now compare finite number of points in the feasible region. But not only that, now in simplex method, you know, you can start from any point in the feasible region and then you have to move in certain direction as a descent direction, you can tell, that minimizes, if it is a minimization problem, so you can move either in this direction or this direction. So you move in a direction which will minimize the value of the objective function. So suppose you move in this direction and you know that, okay, moving in this direction will minimize the value of the objective function more than moving in this direction. So what you do, you move in this direction and then go to the next corner point feasible solution, and then what you do, and then you again test optimality, that is it possible to move in certain direction such that it will decrease the value of the objective function. If it is so, then you move again here, you reach here, and at this point, suppose this is A, B, C, D and E, so at this point C, you observe that you don't have to move. If you move in the direction of D, it will not reduce the value of the objective function. So what you know that then you can have, with some results of linear programming or simplex method, that C is the optimal solution. So now again you don't have to compare all the points, even corner points, but you have to just compare 3 points. Okay, so maybe this 40% of the work has been reduced even with this results. So that is why these optimality conditions are very important, because it helps us to rectify the feasible reason, and from that feasible reason you can have certain points which may be an optimal solution subject to certain conditions, right? So one important thing that is used for having these optimal solutions or optimal conditions, we start with this indicator functions. So basically we start with this minimization problem. To minimize f of x subject to x is in some set, convex set, subset of Rn. So let us tell it P. So this is a minimization problem. We start with this minimization problem, and okay, if this set C is Rn, then it is an unconstrained optimization problem. So if C is equal to Rn, then we talk about unconstrained optimization. And then we can use different algorithms to find out solution of this unconstrained optimization problem. But since we have this constraint set C, which is a subset of Rn, and we don't know what is the structure of this set C, we are in the constraint optimization problem. So we can impose certain conditions on this set C to have a specific type of optimization problem. So suppose this function f is, so f is a function from, you can say, Rn to R. This is an objective function, and this is a convex objective function, convex. So if it is a convex function and this set C is a convex set, C subset of Rn is also convex, then we have this convex optimization problem, right? So what we can do, then we can apply the methods of convex optimization problem to find out a solution of this problem. Yes. Okay. So let me, maybe it's in airplane mode now. So this indicator function is used to convert this constraint optimization problem into an unconstant optimization problem. And then we can apply the methods of unconstant optimization to find out solution of this problem. So let us define this indicator function. Let C be a subset of Rn. So the indicator function of C so it is denoted by, so we can write I of C, I of C is, so this is I of C, so the value at any point x is 0 if x belongs to C, and it is plus infinity if x does not belongs to C, right? So now actually we have defined this function all over Rn, right? So this is a function from Rn to R. So indicator function is a function from Rn to R. Now the next thing is that we observe that this indicator function is a convex function when the set C is a convex set, right? So the indicator function IC x is a convex function if and only if you have C is a convex set. So this may not be always the case, but if this set C is convex, then we have this indicator function as a convex function. So maybe we try to have a sketch of the proof. So suppose we have this, we can have different cases because we have this set C and all of this space outside this set C. Okay, and now indicator function is defined over all this space. So we can have different cases that this we can have, because to show that this function is a convex function, we need the convex combination of 2 points in a space. So the possibilities are that x1 and x2 are in C. If both these points are in C, then we have, by the definition of convexity, we can that implies that lambda x1 plus 1 minus lambda x2 belongs to C. Both will belongs to C, and then we can apply, and this is for every lambda in 0 1, and then we can apply this inequality, right? So then we have this indicator function over lambda x1 plus 1 minus lambda x2. So we have to show that this is less than or equal to lambda indicator function of x1 plus 1 minus lambda indicator function at x2, right? But this point belongs to C, so it will be 0. This point belongs to C, any point in between x1 and x2, so this value will be 0. This is also in C, x1 is also in C, so this is also 0 and this is also 0, right? So this inequality is satisfied when these 2 points are in the set C. Now what other cases we can have? So this case 2, that one of the point Okay, suppose both of these points are outside C. x1 and x2 both are outside C. So what will happen? Then this, so if both of them are outside C, then their convex combination may not be in outside. So it is possible that their convex combination is either outside C or inside C. There are two possibilities, right? So if we have these two cases, so the second one, suppose if x1 belongs to C and x2 does not belongs to C, then we have these two possibilities, that then this lambda x1 plus 1 minus lambda x2 belongs to C, may belongs to C. Then either we have this belongs to C, or lambda x1 plus 1 minus lambda x2 does not belongs to C for some lambda in 0, 1. Right? So then in case that this belongs to C, we can write this inequality, then indicator function of C lambda x plus 1 minus lambda y. So let us try to test whether this inequality is satisfied in this case or not. Right? So this this value, if it is in C, then it will be belongs to C and then it will be 0, right? And what about this? This is x1. I have x2, x1 and x2. Have I done the same? No, here it is correct. So this value will be 0, and what about this? Plus infinity. Again the inequality is satisfied because 0 is less than equal to plus infinity, right? So in this way we can check the other possibility as well, that or what is the case that it does not belongs to C, then indicator function lambda x1 plus 1 minus lambda x2 is less than or equal to lambda indicator function of x1 plus 1 minus lambda indicator function at x2. So you see that this value is does not belongs to C, right? So this is plus infinity, and this value will be 0, and this value will be plus infinity. So again this inequality is satisfied. Okay. And what will be the remaining case? Case 3. Again you can see, similarly you can prove that both the points x1 and x2 does not belongs to C. Then either their convex combination will be in C or outside C, and then we have this two cases. Okay. So similarly you can prove this. So now what we have seen, that this indicator function is actually a convex function if the set C is convex, right? So I mean, if C is convex, then indicator function is a convex function. Now this will be used, but before using that for the optimality conditions, we need another concept of normal cones. So let me briefly define this normal cone, because Professor Mishra has gave some idea about convex cones, and we have seen that how we can identify convex cones by using characterization of convex cones. So so what do we mean by a normal cone? So the normal cone to a set, suppose C in Rn, if and only if. So okay, you try to prove this. You try to prove the converse, right? Because I have proved only one part, that if the set C is convex, then their indicator function is a convex function. So if the indicator function is a convex function, we have to prove that the set C is a convex set. So you just try to prove that, right? Because I think we need only this part, but the converse will be interesting. So the normal cone to a set C, which is a subset of Rn at x, at a point x in C, is given by, so we defined it like this: some vector in Rn such that this v y minus x is less than or equal to 0 for every y in C, right? This is the definition of a normal cone, and so basically what it is saying, that if you have a point x in any place, suppose we have this positive orthenth of Rn, and then at this point you have the origin, right? And then you have to find out all the vectors so that this value, that is the inner product, is less than equal to 0, right? So you will see that at this origin, if you have all the vectors, you can verify also. So this will be the normal cone. So if this is the set C at the origin, you can find out this, right? So now we will see that this normal cone, I mean this is true for this is defined for any set C, but now if the set C is a convex set, then what will happen? So I will state few properties, but I will not prove it. The normal cone to a convex set at a point is also convex, right? The second one is, it is a closed set. The normal cone is a closed set. So we can have a sequence in the normal cone, and it will converge to a point which is also in the normal cone. It contains the origin. And if this point x is in interior of C, then this normal cone will be singleton 0. Okay. So you can use the definition of normal cone to find out whether this results are correct or not. Now we want to find out this find out the subdifferential of this indicator function. because it will be used for the optimality condition. And in that we will, because we have seen that this indicator function is a convex function when the set C is a convex set. So now we can find out the subdifferential of the indicator function. So this subdifferential of this indicator function at any point x bar is defined as, so suppose it is x star in Rn such that this ICX minus ICX bar, this must be greater than equal to x star x minus x bar, and this is true for every x in Rn. Why? Because it is defined over all of Rn. Indicator function, the domain is all of Rn, so it should be all of Rn. Now we may have two conditions when this x bar belongs to C and when this x bar is outside C, right? This is the definition of the subdifferential. Yeah. So we see that this angle, okay, so suppose we have a set and at this point x we want to have the normal cone to this set C, so y is any vector, right? Suppose this is the vector y anywhere in the set. So now we want a vector v, which may, so what is this angle? This is the angle should be more than 90 degree, right? Yes, obtuse angle. So we want a vector v which will make, so suppose we have this angle is 90 degree. So we want a vector v which will be making an angle which is more than 90 degree, right? This is the vector v. Okay, so one vector we have received, one vector which will make, this is more than 90 degree. But now this must be true for every y in C. So when we fixed y, we get a collection of vectors, right? For a fixed y, we get a collection of vectors. And then when we change this y all over this set, so for every y we have a collection of v. And then what we do, we take intersection of all those v's. So that intersection will be the normal cone at that point. Okay, because there are many y's in this set C. It seems like this, like at this point you see, suppose we take this positive orthant of R2, right? So we have this is the tangent, and then this is the outward direction which gives you the normal direction. Okay, like any space you have this tangent direction and this is the normal direction. So basically it is the collection of all the normal directions at that point. If you have any space, any object, at that object you have a tangent space and then you have the normal direction. So this is the collection of all the normal directions at that point. Okay. So with this concept of, yeah. Which one? From here? This should be, you have many directions, na? Yes, that will, yes, that will be this that will be normal to the perpendicular to the tangent. Yes, so you have this tangent, and then when you take the intersection you will have this. Okay, yes, because you have a tangent space and the normal to the tangent at that point. Okay, that will be the collection of normal vectors. That will be the normal cone basically, right? But this may not be the case always, because the structure of the space may change, but then you have to take the intersection of all these vectors. Is it okay? So now we want to find out this subdifferential of this indicator function. So the first case is if this x bar belongs to C and x also belongs to C, then what will happen? Then you see this, according to this definition, this x belongs to C and x bar also belongs to C, so we will have 0 minus 0, which is greater than or equal to this x star. This is x star and x minus x bar. X minus x bar, right? And this should be true for every x in C. I mean, for every x here, if x is in C, right? So, okay. But you see, that is this x star, x minus x bar is less than equal to 0. And this is the definition of normal cone, right? So if this x is in C, then we are having this subdifferential will be same as the normal cone, right? That is x star belongs to the normal cone to C at x bar, right? This is one thing. Now if this x does not belongs to C, then what will happen? If x bar belongs to C and x does not belongs to C, then because we need the condition for every x in Rn. So we have divided Rn into two parts. One part is containing the C and other part is the space outside C. So if it is not in C, then what will happen? Then again from this definition, indicator function of C at x, so this x is outside C, this will be plus infinity, and then we have this is 0 and this is greater than or equal to x star x minus x bar, right? But you see this value is less than equal to plus infinity, which is true always. So it means that this x star belongs to Rn. But then we need the intersection of both these sets, because it should be true for every x in Rn. So if you take the intersection of both these sets, you will have indicator function of C at x bar, and the subdifferential, this will be equal to normal cone to C at x bar. Of course, x bar belongs to C. Okay. Now, if x bar is not in C, you try to find out the result. That कहाँ पे? ये this one. X star belongs to Rn. So when it is Rn, so when this x is not in C, and when it is in NC, normal cone to C at x bar, when this x is in C. But for this we need, it should be true for every x in Rn. The result should be true for every x in Rn. Okay, so which x star we can take? Which will be the intersection of both these sets. So that is normal cone to C at x bar, right? So that is why we are taking, but this is true when x bar belongs to C. If x bar is outside C, you can try to find out that what will happen. Okay.
Normally, pressure differential is defined only at points of the effective domain of the function.
Okay.
If you extend as you are trying to do outside C, then when trying to prove this inequality, you will have troubles on the left-hand side with plus infinity minus plus infinity, which is undefined. For the reason it's not convenient
Yes.
to define the subdifferential
Outside C. Outside C. So that will be the problem because we have this plus infinity there. Yes. 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 So we only need this this value at x at the points which are in the set C, because we are dealing with convex optimization problem, right? So outside C it will not be required. Yes, 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 yes. So now with these two things we can move to this convex optimization problem. Because we have seen when the notion of subdifferential was introduced, that if 0 belongs to f at x bar, this is the first, the subdifferential of f at x bar, so it means that it is equivalent of saying that f of x minus f of x bar is greater than equal to x star x minus x bar, right? And this is I mean for every x, maybe in Rn. Yeah. Yes, but x star is 0, so that will be 0. So and then it will be equivalent of saying that f of x is greater than f of x bar for every x in Rn, right? So this when we have this 0 belongs to the subdifferential of f at x bar, it tells that x bar is an optimal solution. X bar, which is equivalent of saying that x bar minimizes or maximizes, minimizes this f over Rn, right? So this is the first optimality condition that we can have, and if the function is differentiable, then this will be the gradient, that is the Fermat's rule we know, right? So this is the first optimality condition for unconstant optimization. right? For unconstant optimization, we have this condition, which is the first optimality condition. Now we are dealing with this problem of minimize f of x subject to x belongs to C, which is a subset of Rn, and this f is convex. So convex optimization problem, and this set C is also convex, right? So the result is that if x bar in C is an optimal solution of P, then this 0 belongs to the subdifferential of f at x bar, and then we have this normal cone to C at x bar. So now we need this normal cones, because then we will reduce this problem by using indicator function to an unconstant optimization problem. Okay, so this problem to minimize can be written as x bar is an optimal solution of P, and this is equivalent of saying that x bar is an optimal solution of the following problem. So suppose it is P dash. So we want to minimize some function g of x, which is defined as f of x plus this indicator function. Okay, so indicator function of C at x. And then we can write it as x belongs to Rn. So now we have an unconstant optimization problem. Starting from the constant optimization problem, we have converted it into an unconstant optimization problem, and we can see that this function, because if x is not in C, then this value is plus infinity, and it can never attain the minimum value. So all the points outside C cannot be a candidate for a minimum value. Now if it is in C, then this value will be 0, and the minimum value of g of x will be same as the minimum value of f of x. So, but with this trick, what we have done, we have converted the constant optimization problem into a unconstant optimization problem. So now, with this unconstant optimization problem, we have the result. 0 belongs to the subdifferential of that problem. So we can say that this 0 must belong to the subdifferential of g of x. Yes. Sorry, x bar. So x bar is an optimal solution. Now, by the calculus of sum of two functions, because this function is a convex function and this indicator function is also a convex function over the feasible region. So now we can write this is actually equal to the subdifferential of f at x bar and the subdifferential of the indicator function at x bar, right? But what is the subdifferential of the indicator function at x bar? So we have seen that this is actually normal cone to C at x bar, right? And this is the result. So now by using this notion of indicator functions, we could find out an optimality condition. So this is another optimality condition for this convex optimization problem, and that is this okay, so 0 belongs to the subdifferential of f at x bar and normal cone to C at x bar, right? So this is an optimality condition for the convex optimization problem, where function f is convex and the constant set C is also convex, right? Now we can further explore if the set C has some spatial structure. Suppose this set C is, yes. Yes. Outside of C? Yes, outside this C, the value of indicator function is plus infinity. No, outside C, we don't know about fx because we don't have. Yes. Fx will be minus infinity? No. No, this we cannot tell anything about that, right? Because we are dealing with another function g of x, which is defined like this. Okay, so you are telling that what will be the value of f of x outside f of x is defined over Rn. F is defined over Rn, right? Here f is defined over Rn. We are not defining f over C only, it is defined over Rn. Suppose it is some function x1 square plus x2 square. But then the feasible reason is a set C which may be Rn, may not be Rn, right? Suppose we want to minimize x1 square plus x2 square over a set which does not contain the origin, right? Then the unconstrained optimal f is defined on Rn, f is defined on all this, but otherwise this sum is not defined. If f is not defined on Rn, then this sum is not defined. Yes. Yes, that can be, but this is well defined. This is well defined, right? So we don't have to bother about whether f is defined over C or not. Even if it is defined over C, we can extend by using this indicator function. That is why we are using this indicator function, right? Yeah.
It's even true.
Yeah.
If f is extended real value, if you allow f to take the value
plus infinity. Okay. So if we add here r union plus infinity also, this will work. Because then again it will be like some values will be plus infinity. Yes. Is yes. Okay. So now we want to discuss some spatial structure of this problem, and this is minimization of f of x subject to some gix less than equal to 0 for every I in some set, suppose M 1 to M, right? And we keep this subset C of Rn which is convex, right? So Okay, so all these functions f and gi, these are defined from Rn to R, and we can add also plus infinity, right? So these are convex, and this set C is also convex, right? And you can have this exercise. We have had this exercise that if this set Gix is convex, functions are convex, then this inequalities will give you a convex set, right? And then with this convex set and with this convex set, intersection of two convex sets will also be a convex set. So it is actually a convex optimization problem, but along with we have some inequalities to define the feasible region. Okay. So for this we need okay, so what will be the feasible region? The feasible region is given by f, which is x in Rn, such that this Gix is less than equal to 0, I is in M, and x is in C, right? And then we talk about active indices. Yes? This one? It should be if and only if, because this is a convex optimization problem, right? But if you remove the convexity, it may not be true. If you remove the convexity, it may not be true, right? So if you have convexity, you can prove the converse also. Now this, so suppose we have this constraints, functions, and this is 1, this is 2, this one is 3. So you see at certain points, at here and here and here, at this point the inequality 1 and inequality 2 are active. So we don't have to bother about this third one. At this point 3 and 2 are active. At this point this 1 and 3 are active, right? So at a certain point of the feasible region, the set of all the active constants at x bar in F is given by, so we can write it like M at x bar, right? So this will be some indices in M such that Gi x bar is equal to 0. So all the active constants, so suppose we have 3 constants, but this is the point x bar, then 1 and 2 are active. So out of M we will take the indices 1 and 2. Similarly for different points we can have this different indices. It can also be empty. Suppose we have a point here, then no constant is on the boundary, so this is empty, right? So now based on this active indices, we can give you a necessary optimality condition. If x bar is in F is an optimal solution of F over F then there exist Lagrange multipliers. So we take this lambda naught and lambda 1, and we have m, lambda m. These are greater than equal to 0, not all 0. Such that this 0 belongs to and we can have this summation of lambda I equal to 1 to m subdifferential of gi at x bar, and then we have this normal cone to c at x bar. And along with this, we have this complementarity conditions gi x bar is equal to 0 for every I in M. Right? So, this is a necessary optimality condition which is popularly known as Fridge-John type necessary optimality condition, because in this multiplier we have a multiplier lambda naught along with this objective function which can also be 0. Okay. So, we will see that how we can improve that condition by using a constant qualification, and then from this we can have a Karush-Kantaka type necessary optimality condition. Yes? Here it can be 0 also. Yes, this is the problem with this optimality condition, right? Because we have, if this lambda naught is equal to 0, then this is true for any objective function with the same feasible reason. Okay, so then it will be useless. So to have a condition when this lambda naught is not equal to 0, we have to impose certain conditions on the feasible reason, which we call as constant qualification. So we will see that how we can use some constant qualification to have this condition lambda naught not equal to 0. Right? So, okay. So let x bar in F be an optimal solution of this problem P dash. Now again we are going to define a function phi from Rn to R such that phi of x is defined like max of f of x minus f of x bar and g1x and gmx for every x in Rn, right. So all these functions are defined, fx and g, so we can define a max of all these functions. So this is a max function, and we haven't done this exercise, but you can see that this is all of these are convex functions. So max of finite number of convex functions will also be a convex function. So we have to observe that this phi is a convex function, right? you can do this exercise that if all the functions are convex, then the max will also be convex. So you can use this definition of convex functions and then try to prove this result. So this is a convex function. Now you observe that this phi of x bar is equal to 0, right? Because if you have x bar, this is 0, this will be 0 when x bar is, if you have x bar in place of x, and then g1 of x bar is less than equal to 0, gm of x bar is less than equal to 0. So the maximum value is obtained at 0. So this phi of x bar is equal to 0. And then x bar is an optimal solution of this optimization problem of minimization of this phi of x subject to x in this set C or the feasible region F, right? That is, phi of x bar is less than equal to this phi of x for every x in the set of all feasible regions. So we will have two conditions, that if for any x in F, this gi of x less than equal to 0, I mean it should not be F, it is the set C, okay, even Rn. So because we are going to have two conditions when this gix is less than equal to 0 and gix is greater than 0. So if gix is less than, because when it is in C, it may happen that gix is less than equal to 0 or gix is greater than 0. So if gix is less than equal to 0 for every I in M, then this x belongs to F, right? And hence you have f of x bar is less than equal to f of x, which implies that this phi of x is greater than equal to 0, which is equal to phi of x bar, right? Phi of x bar. I think it should be C here. Okay. F of x, because there we have f of x minus f of x bar. So f of x minus f of x bar will be less than equal to 0. And all this gix is also less than equal to 0. So the maximum value is 0. So this will be greater than equal to 0, which is equal to phi of x bar. So this minimizes when x is in C. Now if for any x in C, gi of x is greater than 0 for some I in M. at least one I. If this inequality is violated, then this phi of x is strictly greater than 0, which is again phi of x bar, right? So if you combine both these conditions, either it is in C, so if it is outside this C, I mean it is phi is defined all over Rn. So if it is outside this C, so now this x bar is an unconstant optimal solution of phi over Rn, right? So that tells that x bar minimizes phi over Rn. And now you have the result. What? Optimality conditions in terms of, actually not Rn, because over C. Okay. So by the optimality condition, or simply we can write that implies this 0 belongs to the subdifferential of phi at x bar. We can add normal cone to C at x bar, right? And now it remaining to define just one function. If we define something like g naught, which is defined at this first function f of x minus f of x bar, right? X in Rn. Then actually this phi is the max of, phi is the max of all these convex functions. So this phi of x can be written as max of all this g, suppose gjx, where this j is from 0, or we can write it here like we can add 0 union m, right? And we have one observation that the max of convex functions is also a convex function. So this phi is a convex function. And if it is a convex function, we can find out, even if it is not a convex function, so you can do this exercise, but that implies that phi is a convex function, right? And if phi is a convex function, you observe one thing, that if you define one set like this, I of x bar is equal to I from 0 to m, such that gi of x bar is equal to phi of x bar, which is equal to 0. Right? I mean here gi also contains the function f of x minus f of x bar. So it is possible that at this point x bar, so phi of x bar will be some function, will take some functional values. For example, we have this function, so it is actually max of these two functions, right? So this is, suppose this is g1 and this is g2, okay? So at this point it takes both the values of g1 and g2, right? So then this index will contain both 1 and 2. But if you talk about this point maybe, so it contains the value of g1 only, so you have to take 1. At this point it contains the value of g2 only, so it takes 2, right? So like this we have to work out this index. So this I of x bar is equal to 0 union, we have defined this m of x bar earlier, so it contains this including 0. 0 is the first index which is associated with the objective function m, right? So now just we have to use this condition of optimality. So 0 belongs to, so what will be the condition? So we can write that this 0 belongs to this subdifferential of phi f x bar plus normal cone to C at x bar, right? But what will be this? So now for the max function we can have a subdifferential. I am not going to prove it, I will write down the result because proving it will take a lot of time. But then we can write it in terms of convex hull. That in one of the lectures were described that any set, if you have any set like this, so what is the convex hull of this set? It is the smallest convex set which contains this set. So maybe this will be the smallest convex set, but how you construct it? It is the convex combination of all its points, right? So you will generate this set. So convex hull of any set is the convex combination of all its points, right? So this will be 0 belongs to the convex hull of this set. This will be the subdifferential of G naught at x bar, and then you take the union, and this is union of subdifferential of Gi at x bar, and what is I? I is in m of x bar, right? So you take all these things, convex hull, and then you have this normal cone, C at x bar, right? And this actually tells about the result we wanted to prove. It is immediate from this because this is the convex hull. It means there will be multipliers which will be greater than equal to 0, and so there will be multipliers. There exists lambda naught and lambda 1 and then lambda f such greater than equal to 0, and this summation of lambda I is in m and lambda naught is equal to 1 because of the convex hull. M of x bar. Yes, m of x bar. Thank you. So this is 1. It means, so this 1 tells that all of these multipliers cannot be equal to 0 simultaneously, right? So in the result we don't write this, but it tells that all these multipliers cannot be equal to 0 simultaneously. Okay, so this multipliers will be there such that we can write it like this, that 0 belongs to this first one, lambda naught subdifferential of G naught x bar plus lambda 1, and then we can have the summation lambda I subdifferential of Gi at x bar. I is in m of x bar, right? And then the normal cone to C at x bar. Okay, and then all of this. And now if we choose lambda I equal to 0 when I does not belongs to m of x bar, if it is outside m of x bar, then we can write this Gi x bar is equal to 0 for every I in m. Because if it is in m of x bar, gi x bar will be 0, and if it is not, if gi x bar is not equal to 0, we will take lambda I equal to 0, right? So from this concept of convex hulls, we can have this directly. But the problem now, it is the Fritz-John type necessary optimality condition, and with the function we have lambda, we may have lambda not equal to 0. So to rectify that, we need constant qualifications. So maybe in the next tutorial we can try to find out some constant qualifications which will give a condition which is known as Karush-Kantegar type necessary optimality condition.
Just a comment.
Yes, please.
Once you introduce lambda I equals 0
Okay.
for the non-active constraints, then the summation is
Over m, yes. So then we have to set setting lambda I equal to 0 when I does not belongs to m of x bar, and then this will be replaced by m. Okay. And I think in the statement we have m in place of m of x bar in the statement of the theorem. So this is the most important result, because we are dealing with optimality conditions of different types of optimization problems, and we often come across this type of KKT conditions or Fritz-John conditions, and then these conditions are actually used to construct algorithms to find out solutions of a given optimization problem, right? Okay. Yes.
स्लाइड्स में मेंशन किया था कि fx अगर मेरा फंक्शंस कन्वेक्स होगा तो c को कन्वेक्स होना ही पड़ेगा. ये हमेशा ट्रू
नहीं, कन्वेक्स होना पड़ेगा नहीं. दिस इज अ कॉन्वेक्स सेट.
ऐसी कन्वेक्स सेट होगा.
Yes, we are taking a convex optimization problem where the function is convex and the feasible region is also convex.
बट मैं ये पूछा था जैसे मेरा fx हम यूक्लिडियन नॉर्म में डिस्टेंस मिनिमाइज करना है और c नॉन कन्वेक्स है.
Then we cannot apply this result because the indicator function will not be a convex set. ये पूरा जो process है, then you cannot apply these things. Then you have to apply certain other formulations of non-convex optimization.
इसके वजह से ऐसे ब्यूटीफुल अगर फंक्शंस अगर fx होगा तो c कन्वेक्स.
That is another thing. That is another thing. Domain of the function, if it is convex, then its domain will be convex set. That is a result in that book of Chuang. You can search for that, right? Because otherwise we cannot define a convex function. Because we need lambda x plus 1 minus lambda y must be in that set. If it is not in that set, we cannot define a convex function. That is why the domain of the function must be a convex. But here it is not the domain of the function. Here C is the feasible region of the optimization problem, right? So that is a different thing. Domain, and so domain must be convex, otherwise we cannot define. And here we are taking the domain all of Rn, so that is obviously convex, right? Okay. Thank you. So we will meet tomorrow at 10 to resume, and tomorrow you will have the first assessment. So be prepared.